Good morning, everyone. This is the last report. Thank you very much to this great opportunity. Yeah, I want to give me this great opportunity to introduce our work. Yeah, this obviously is ambition. So the most important, I want to introduce our new work on the slope adaptive waveform matrix. This is the outline. We know that this figure is mostly used to begin the story of global carbon. We know that carbon dioxide accumulates year by year in the atmosphere. So due to the effect of greenhouse effect, it will alter the water cycle or the energy balance. So then further reduce to the global climate change. So the most important one is that in the carbon balance, the land surface is the most complicated sources. So I think most of you should agree that forest is very important, no matter in the coverage area or the volume of carbon storage. So the monitor on the forest change is very important. So we know that previous several reports have shown us that there are several new missions for monitoring the carbon storage, including the GEDI, the MOLI, and the SI2. In China, we have two satellites carrying the LiDAR sensor. One is we call in Chinese called Gaofen GF7. It will carry two laser pulse. It's mainly designed for the measurement of terrestrial vision. Another one, we call it terrestrial ecosystem carbon inventory satellite. It carries three laser pulses to specifically designed for Malheur forest. So we know that typically over flat terrain, we always use the ground peak as a reference to define several energy percentile metrics to use it for biomass estimation. However, we can see that when the same forest is standing on different terrain slopes, the ground peak will mix together with the canopy peak. So even though we use the decomposed Gaussian peak, it's really difficult to extract the correct metrics. So based on the literary review, we can see that in most global products, most laser ISAT data standing on the slope higher than 5 degrees are always discarded. So it's still a challenge from my view. We know that most laser waveforms take the form of Gaussian function. It can express like this way. When it's returned by the inclined plane, it can be modeled like this. We know that the terrain slope extending the waveform length. We know that the sigma controls the width of the pulse. So we propose this function to model the waveform or inclined background. Here it related with the original pulse length, pulse width, and the footprint size and the terrain slopes. So we can see that this is the figure. The blue is the simulated waveform of forest, and the red one is the background waveform calculated using this model with the same terrain slope. We can see that when these two waveforms are aligned by the signal ending point, the ground waveform will be extended in the same way as waveform. So we guess it may be if we use the calculated background waveform as a reference, so the extension effect may be relieved. So here we propose a new matrix. Firstly, we can, but taking the signal ending point as a reference, we firstly define the regular energy percentiles like RH 25, 15, 75, and so on. And for the calculated background, we also can define HG 15, 75, and so on. So their difference should be we call it the slope adaptive waveform matrix. This method is composed by 2 points. The first is the model is for the inclined plane. Another way is the two waveforms that makes aliened by the signal ending point. So we call this method as pipe. So this it has been published on the RSE. Now we further validated the new metrics using the simulated waveform. When we used the forest growth model, ZLIG, to simulate a series of forest stand, and then feed it into the LiDAR waveform model developed by Professor Guoqing and Rensen around 2000. And in the simulation, we changed the terrain slope from 0 to 14, and in a step of 2 degree. And we simulated 2 footprint size, including 25 meter and 70 meter. So totally, we simulated 16,800 waveforms. And say these are typical or representative simulated waveform. Because this 25 footprint and 70 footprint. We can say for the 70 meter footprint size, like eyesight, we can see that around about 10 to 20 degree, the ground peak and the canopy peak will mix together. But for smaller footprint, okay, it looks better. It's always mixed together between 30 and 40 degree. But this one is the window for typically when they mix together, we mostly try to decompose the waveform into several Gaussian peaks. We can see that the decomposed peak is in fact very complicated. We further use these metrics to try to estimate the forest biomass. This one is use the Gaussian decomposition. This one is use the waveform parameter, including the lead 10, chill 10, and the waveform length. And this one is our new metrics. We can see that for both 25 and 70 meter footprint size, the pipe looks much better than these two types of metrics, including the dynamics. This dynamic is mostly caused by the terrain slopes. Okay, the character is too small. Okay, we further validated the metrics using the real asset data. Firstly, we do initial tests in China, in southeastern China, using 26 waveforms. Here listed some 3 representative waveforms. This one is obviously the sparse forest on flat terrain, and this one is also sparse forest on steep terrain, and this is medium forest on mountainous area. You can see that the red one is calculated waveform. You can see it's matched the waveform very well, and for the Gaussian decomposition, you can see the Gaussian peaks is very complicated. So as to overall the overall estimation accuracy, we can see that the pipe performed better compared with GEDI and web. So based on these results, I'm wondering whether we can directly produce the global product of these new metrics. So thanks to the great data from NASA GLAS, they fly several sites along the GLAS tracks. There are several. I learned about more than 1,000 waveforms, and okay, we can see that as for in ideal conditions, we can see that the blue is the asset signal, and the red one is the calculated bareground waveform with the given terrain slope read from SRTM. We can see that okay, over this sparse forest or nearly bareground, the proposed model can match well with the ground peak. And as to the complicated mountainous areas, we can see if we only see this waveform, we cannot figure out where is the ground peak. So if we use this, okay, we can see the green one is the ground digital terrain model from GLAS. So we can see that the ground peak simulated using our model can match very well. So over this circumstance, the PEM method performed very well. But we also observed several expectations. The first one is over the dense forest stand. We can see that the red, the black line is given by the GL14, and this is the signal ending point, signal beginning point, signal ending point. We can see that in fact the waveform cannot penetrate the canopy. It's too dense. So I think pipe can do nothing for it. I think the most important way is whether the one way for us is to whether we can find some sign to identify which is the unpenetrated waveforms. Another way is in the new standard we need to enlarge the power, use a larger power. Maybe this problem can be solved. Another one is the multiple scattering. We can see that the same as before. The green one is the terrain position given by the GLAS. You can see there's a long trails here. I think, as for myself, to my understanding, it should be caused by multiple scattering. So this is also a bigger problem for the pipe. So we need develop a new method to get correct estimation of signal ending point. So I think to the multiple scattering, the waveform fluctuation is obviously severe. So it is whether this one can be used as a sign to identify these waveforms. It maybe work. Another way also is the saturated waveform. We can see that when, according to our observation, when there is water in the footprint, like here, 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 and here, the saturation waveform always saturated. So for saturated waveform, I think maybe the signal above the saturation point is useful, and below that should be discarded. Okay, this is the whole report. I think our new method provides a solution for the relief terrain effect if the terrain is not too complicated. But when we, based on our learning from our 2A waveforms, we found full effect about the penetration capability, signal saturation, multiple scattering, and terrain effect. We should specifically these full cases. And to the penetration capability, I think is still a biggest challenge, not only for the large footprint. When we see ISAT 2, it's still a big problem over tropical area. So I think it's a common challenge. Saturation signal, I think it's not difficult to identify these waveforms, and it's not difficult to direct the related metrics. And multiple scattering should be given special care, consideration in the future. Okay, thank you.